Today we're going to be talking about composite functions, and by that we mean functions inside of other functions. Before we start talking about those, though, we're going to quickly review some algebraic operations with functions. This is something that hopefully you were exposed to during intermediate algebra, and if you feel like you want even more instruction on that, I encourage you to take a look at your textbook. And most of this video is going to focus on composite functions, since that is likely the more new concept to you. As always, please feel free to go ahead and use the timestamps located in the description of this video if there's a particular topic that you're wanting to jump to. Now, first of all, what do we mean by algebraic operations with functions? So a lot of times as a shorthand, instead of explicitly saying I'll do one function plus another function, we'll actually just put the operation right there in between in parentheses f plus g of x in this example. And you just a lot of times want to translate that to that operation really being outside, talking about those two functions having that operation going on. For multiplication, typically, just like whenever we say 3x, that means 3 times x. A lot of times we'll just say fgx, meaning f of x times g of x. Occasionally, you'll also see a closed-in dot instead to note multiplication. And the fact that that dot is closed in is actually going to be super important here whenever we're talking about composition of functions, because if it's talking about multiplication, we're going to talk about a closed dot in between the f and the g, or we're just talking about the f and g right next to each other. And for division, as always, you want to think about domain, and for domain, we're never allowed to divide by 0, so you want to always make sure that denominator is not equal to 0. So let's just practice using these algebraic operations a little bit. So for example, if we have g minus f in parentheses of x, that means that whatever comes first, in this case g of x, we're going to subtract f of x from. Now, a lot of times I want to put parentheses around that f of x to keep in mind that that subtraction is applied to the entire function. Then I'm actually going to replace these with what these are. So g of x is equal to x squared minus 1, according to the directions here, minus an f of x in parentheses is equal to x minus 1, also there in the directions. The reason why I use those parentheses is you want to keep in mind that minus is distributed to the x and to the negative 1. So I'm going to drop down x squared minus 1 and then minus, so negative 1 times 1x gives us minus x. Negative 1 times negative 1 gives us plus 1. Where minusing a negative 1 becomes adding a positive 1. And then you probably do want to combine like terms. So are there any like terms we can combine here? There are. Negative 1 plus positive 1 makes 0, so I'm just left with x squared minus x, and I'll call it a day. Go ahead and try the next one yourself. See if you can translate this notation into what's going on with these specific functions. So a fraction, remember, is the same thing as division. So in this case, we're doing g of x divided by f of x. G of x is equal to x squared minus 1. F of x is equal to x minus 1. And that is technically correct. It's possible they might want to see if this simplifies a little bit. In order to see if this simplifies, you want to ask yourself if either the numerator or denominator factors so that something can potentially be canceled out. In this case, our denominator, x minus 1, there's no greatest common factor there besides positive 1. We're good. That doesn't factor further. But what about that numerator? How does that factor? Remember, that's really secretly x squared plus no x's minus 1, so we're asking ourselves what multiplies to negative 1 and adds to 0. And since it's a leading coefficient of 1 in front of that x squared, I can jump straight to parentheses and say that positive 1 and negative 1 will multiply to negative 1 and add to 0. So I have an x minus 1 and an x plus 1, all divided by still x minus 1. Then you want to ask yourself what's going to simplify. Well, if I have x minus 1 divided by x minus 1, that cancels to make 1, and I'm just left with x plus 1. Although originally still domain-wise, that occurs with the original function, so x is not allowed to equal positive 1 because of that original. So our domain would be negative infinity to positive 1, union positive 1 to infinity to indicate that on a number line, I would be skipping over the value positive 1 and that all other numbers are allowed. The domain of these types of rational functions is something we'll be emphasizing even more later in this course when we formally think about rational functions, but it is something you should always keep in the back of your mind, that I want to make sure I'm never dividing by 0. and that potentially I can simplify a rational function if there's any factors that are common to both the numerator and denominator, but the domain of the overall function still is from the unsimplified version. Now let's actually get into the meat of this section though. So what is a composite function that we're referencing here? Well, a composite function is basically when you have a function inside of another function. And you'll know it's composite because you'll see that beautiful circle that is not filled in. So keep in mind that f of g of x, noted like this, is not the same thing if I put a closed dot in between. It's just notation, it's just language. So in the mathematical language, in the common notation that we use for math here in the West, we need a open circle that is not filled in to indicate that this is talking about function composition. And every single time I see that function composition, I go ahead and change that to a notation that to me feels a little more intuitive. That instead of noting it with this open circle, I say, okay, that means I'm plugging g of x into f. And that's exactly what we're noting here. So that means everywhere you see an x in f of x, you replace it with g of x. That is exactly what that notation means. Sometimes you'll also hear it called f composed with g at x, or typically in this class we'll use that f of g of x language. So let's take a look at what that looks like in practice. So with this notation, that means that I'm plugging g of 2 into f. So I'm just going to go ahead and rewrite that way. So I'm plugging g of 2 into f. And actually, I'm going to go ahead and change up the color that I'm noting g of 2 on, because in terms of order of operations and keeping yourself straight, whenever you're plugging in a particular number into that inside function, it's actually easiest to go ahead and just evaluate that inside function first and then worry about the outside function. So let's go ahead and do that off to the side. Since we want to plug g of 2 into f, it's going to be helpful to know what g of 2 is. In this case, in order to figure out g of 2, I want to look at the g of x function. And this is telling me plug into everywhere you see an x in g of x. So I'm going to go ahead and do that. So instead of x squared, that becomes 2 squared. That minus 1 doesn't have any x's, so that just stays as is. Now, order of operations wise, I want to first simplify 2 squared. 2 squared is the same thing as 2 times 2, which is 4, minus 1, and then 4 minus 1 gets us 3. So really, this whole thing had been asking us to evaluate again f. I'm just going to set this up real quick. So we're finding f of g of 2. We just figured out g of 2 was 3. And now we just have to worry about that as is, because now I know exactly what I'm plugging into f. So by doing f open circle g of 2, they were saying that's wanting to plug g of 2 into f. We evaluated what g of 2 was off to the side. Now we know that we're plugging really g of 2 is 3, so we're plugging 3 into f. I go to the f of x function, I replace everywhere I see an x with a 3, and then 3 minus 1 gives us 2. I don't know why I just wrote down a 3. It is a 2. 3 minus 1 is 2. Masters in math, everyone. All right, so we have 2, and that's our final answer. Go ahead and pause your video and see if you can go ahead and evaluate the next one yourself. First thing you want to do is note kind of what it is that you want to do, which in this case is, since it's written the other way around, plug f of 2 into g. First thing you want to do is evaluate what f of 2 is off to the side. So that means in the f of x function, plug in 2 for x, so it becomes 2 minus 1. 2 minus 1 gives us 1. Great, we just figured out what the inside function is. So if we're finding g of f of 2, that means that you're going to replace f of 2 with 1. So this is really asking us to find g of 1. Then we can go ahead and evaluate what g of 1 is. We want to look at the g of x function, replace everywhere we see an x with a 1. So we find 1 squared minus 1. 1 squared is 1 times 1, which is 1. 1 minus 1 gives us 0, and that's our final answer. So every single time you have a specific number you're plugging in, plug in that number to the inside function first, evaluate and simplify, then plug that into the outside function. What if you're keeping it as a generic x? That's going to be slightly different. In terms of how you read this notation, that's going to stay the same. So if I'm asking for f of g of x, I know that means I'm plugging g of x into f. And in this case, I know that g of x is x squared minus 1. So I'm really actually going to note that that's actually what I'm plugging into f. Then I want to actually replace this phrase in parentheses everywhere I see an x in f of x. So instead of writing x, I'm going to write x squared minus 1, and then I'm going to drop down the minus 1. Since f of x was equal to x minus 1, I replaced the x with what g of x was, in this case was x squared minus 1. In this case, because this x is by himself, you can sort of think of it as secretly multiplying by just positive 1 on the outside, which even if you distribute it, doesn't really do anything. 1 times x squared is still just x squared, 1 times negative 1 is still minus 1, and then we drop down the minus 1. Had there been any multiplication, division, squaring, whatever done to this x, there would have been something more interesting that happened here, and these parentheses would have actually done something. This is a very rare case where they didn't really do anything because that x was by himself. Technically multiplying by positive 1, but multiplying by positive 1 doesn't really do much. Then you just want to ask yourself, are there any like terms? In this case, negative 1 and negative 1. So x squared minus 2 is our final answer. So notice here it was a little bit different in that I didn't really need to off to the side really evaluate what g of x was. I already knew what it was. It was just x squared minus 1. So there was no plugging in a specific number that had to happen. Go ahead and pause this video and try the next one yourself, and then we'll talk about that. Here you want to note the same thing of I'm plugging in f of x, this time into g of x. And then I want to actually note what f of x is. In this case, f of x is x minus 1. So I want to plug the entire phrase in parentheses of x minus 1 everywhere I see an x in g of x. And this is a case where that'll actually make a little bit more of a difference, because now instead of x squared, I have x minus 1 all squared, and then I'm going to still drop down that minus 1, because that minus 1 doesn't have any x's associated with it. If no particular type of simplification was required, this is technically a function, you're good. It might be a good habit to go ahead and simplify though. To simplify in this case, if there were any like terms I could combine right away, I would want to do that. But be careful, I'm not allowed to combine this negative 1 with this other negative 1 just yet, because this whole entire thing of x minus 1 is being squared. And in terms of order of operations, I have to deal with that first. So I like to remind myself that x minus 1 squared really means I have an x minus 1 times another x minus 1. I'm going to just drop down the other minus 1. Then I'm going to go ahead and distribute this out. So I have an x times x, that gets me x squared. X times negative 1 gets me negative x. Negative 1 times x gets me negative x. Negative 1 times negative 1 gets me positive 1. There's a couple different ways people learn about this. You could maybe hear foiling specifically. I usually just draw these arrows and make sure that if I have 4 things here in parentheses, I better have 4 terms that I have at some point multiplied every combination of these. And then don't forget to still drop down that minus 1 that was outside the parentheses. Now you're going to combine like terms. In this case, I have one here at negative x and negative x means negative 2x, because I'm doing negative 1x plus another negative 1x. Positive 1 and negative 1. 1 minus 1 gets me 0. That doesn't really do anything. My final answer is x squared minus 2. And I shouldn't say it doesn't do anything. 1 minus 1 is 0, so you just don't write it. That is something, I suppose. But our final answer is x squared minus 2. Technically, you could factor out an x if you were feeling still inclined. Not required, though. And this is just giving a recap that you always want to do things with the inside function first. If there's anything in particular you have to plug into that inside function, go ahead and do that and simplify that first. If it's just an x, kind of note what that inside function is, and then plug in the result to the outside function. We can also talk about composite functions specifically from tables and graphs, so equations are not the only way that we could be presented with a function. And at first that might seem a little bit more foreign, but in some ways it's actually less work because you don't have to do any evaluation yourself. You are simply translating the function notation into its result. So this is more like a language translation exercise to understand that math language. So if I have f of g of 2, I want to first note that that means I'm plugging g of 2 into f. So I'm just going to rewrite it exactly with that language. Then just like before, that means I want to actually evaluate what g of 2 is first. So that is asking when x is 2, what is g of x? Because that 2 has taken the place of x. So I go over to my table, find when x is 2, go over to g of x, and I see that that is 4. So this is really asking me to find f of 4 since g of 2 is equal to 4. Then I want to do the second step of actually evaluating what f of 4 is, and that's saying the same sort of thing of now that gave me that x is equal to 4, and they want to know what f of x is equal to. So I go over to my table, find when x is equal to 4, and that means f of x is equal to 1 at that point. Go ahead and pause your video and see if you can evaluate the next one yourself. So this time they flipped around the order. Now they gave us g of f of 4. So that means I want to evaluate f of 4 first, which is actually what I just evaluated earlier, because that's asking us to go over to when x is 4, f of x is 1. So this is asking me to evaluate g of 1 since that inside function evaluates to 1. And then I go back over to my table. When x is 1, g of x is 3. And so my final answer would be 3. You could do the same thing with graphs instead of tables. It's just that instead of locating the x on one part of the table to get the y, you're going to locate the x on the x-axis and then trace up to get the y. That'll be the new order, but it's the same idea. You're just doing a different representation of the function. So just like before, we're first going to note that the inside function is g of 1 in this case. So they're asking us to find f of g of 1. Then I go over to the g of x graph. In this case, the g of x graph was literally listed first, but always double check that your notation matches because it may not be literally listed first. So I go over to the g of x graph, and they're asking us to plug in when x is equal to 1, and then trace up that means g of x is equal to 3. So we're finding f of 3 since g of 1 is equal to 3. Then I go over to my f of x graph and I do the same process. So I go over to when x is equal to 3 this time, trace up and over, and our y value, our f of x value, is then equal to 6 as my final answer. The domain of a composite function is the most common place that people get tripped up because you always have to think of two things. So big picture wise, you first think of the domain of the inside function. Because remember, in terms of order of operations, that's always the first thing you evaluate. So whatever is the domain of the inside function still applies. You still have to follow all those rules. Then you find the domain of your new function, new composite function. Notice you never actually care about the domain of the outside function by himself. You only care about the resulting domain of the outside function after that inside function has been plugged in. So you look at the domain of the inside function, apply that, and you look at the domain of your new composite function, apply that. But never look at the outside function by himself. And that's exactly what we're going to go over in an example. This is written out if you like seeing it written out, but let's actually just do that. So here, if we want to find the domain of f of g of x, so that means that first I care about the domain of the inside function, g of x, which in this case is 3x plus 2. If I just have a good old-fashioned linear function, what is his domain? That's just negative infinity to infinity. So there's really nothing I have to worry about too much about that inside function's domain. And in fact, the domain of the composite function will remain negative infinity to infinity unless there's something else funkier going on with our composite function that I still have to worry about his domain. So let's look at that part. So the domain of the new composite function, well, I don't know the composite function yet, so let's actually find the composite function so that we can know his domain. So if I'm looking at f of g of x, remember that means I'm plugging g of x into f. I probably want to note what g of x is, which in this case is 3x plus 2. And now I'm ready to go ahead and everywhere I see an x in f, replace it with 3x plus 2 in parentheses. So in this case, for x plus 2, instead of writing x, I wrote 3x plus 2, and then I still have that outside plus 2. Then we have 3x plus 2, and then we have that outside minus 1. Here, are the parentheses doing anything particularly interesting? They're actually not, because neither of these x's is multiplied by anything, so they're being secretly multiplied by positive 1, but I'm going to go ahead and rewrite them without the parentheses because we've already sort of secretly multiplied it by positive 1. Then I just want to ask myself, within the numerator or denominator, are there any like terms? There are. In my numerator, I have 2 plus 2 is 4, and in my denominator, I have 2 minus 1 is 1. Now I want to ask myself about the domain of this new composite function. And when I have x's in the denominator, what do I have to worry about? I need to make sure I'm not dividing by 0. So in this case in particular, I want to make sure 3x plus 1 does not equal 0. Notice I never care about x minus 1 not equaling 0. This function, this outside function without g of x in it, is not of any concern to me in this problem. I just care about that inside function and this new composite function, this new function. I want to make sure that I'm not secretly dividing by 0 there, because that would be a problem. So I need to figure out which x values am I not allowed to plug in because it would cause me to divide by 0. So I go ahead and solve for x. I want to undo any addition subtraction first, so I'm going to subtract 1 from both sides. So 3x is now allowed to equal negative 1. Then I want to undo multiplication division, so I undo multiplying by 3 by dividing by 3. 3 divided by 3 makes 1. In this case, I've now noted x is not allowed to equal negative 1 over 3. So on a number line, I have negative 1 over 3, open circle. If there were any restrictions from the inside function, I would also put that on my same number line. I don't have any restrictions from that inside function, so I'm in luck. I just have to worry about this negative 1/3. So my overall domain in interval notation is from negative infinity to negative 1/3, parenthesis because I don't want to include the 1/3, negative 1/3 I should say, and then negative 1/3 to positive infinity. And that is my final domain on the entire composite function. Go ahead and pause this video and see if you can figure out this next one. So the first thing we need to worry about for the domain is the domain of the inside function. So in this case, I'm plugging f of x into g of x. So f of x is my inside function. And when I have a square root, what do I have to worry about for underneath the root? Whatever is underneath the root has to be bigger than or equal to 0, because I can only plug in 0 or positive numbers underneath my root. Otherwise, I'm getting complex numbers. So I need to set up an inequality that 2x minus 3 has to be greater than or equal to 0. Then I want to solve for x. Same sort of order. I first want to worry about undoing any addition subtraction. So undo minus 3 with adding 3. Negative 3 plus 3 makes 0. I have 2x is greater than or equal to positive 3. Then I want to undo any multiplication division, so I divide by 2 on both sides. Do I need to flip around the inequality? In this case, I do not, because I'm dividing by a positive. Had I divided by a negative, I would have had to worry about that. So x has to be bigger than or equal to 3/2. If I wanted to note that in interval notation, that would be 3/2 closed circle all the way out to positive infinity. So for the inside function, we're talking 3/2 to infinity. Now we want to see if there are any further restrictions on the domain from our new composite function. So now let's look at our new composite function. So to find that, we're finding g of f of x. That means I'm plugging f of x into g, which means I'm plugging the square root of 2x minus 3 everywhere I see an x in g of x. I want to plug that in parentheses. So in particular, I have parentheses 2x minus 3 all squared minus 5. And then what happens when I square a square root? For example, if I did the square root of 4 times the square root of 4, that becomes 2 times 2, which is 4. If I do the square root of 9 times the square root of 9, that becomes 3 times 3, which is 9. What pattern do you notice is happening? The squaring a square root undoes each other, because this I should have actually noted at the beginning. Square root of 4 squared is the same thing as square root of 4 times square root of 4. Square root of 9 squared is the same thing as square root of 9 times square root of 9. So a lot of times you just see people cross it out like that, but that's kind of really what's happening, because remember, a square root by definition means, well, what number times itself gives me that, and then you're multiplying that number by itself, so it should give you whatever was underneath the root. So that's exactly what happens here. So I'm left with just 2x minus 3, and then drop down the minus 5. Then you want to ask yourself, are there any like terms? There are. I've got that negative 3 and that negative 5. I can combine. So our final composite function is 2x minus 8. Are there any further restrictions in the domain that come from this? There are not. A good old-fashioned linear function like this, which is what this simplified down to, has no domain restrictions. So I really just have that domain from that inside function. So I need to make sure I'm only plugging in numbers that are 3/2 or bigger. Because remember, order of operations wise, I would still, even though this kind of cancels out, I'm still evaluating that square root first before I'm squaring him. So I'm only allowed to plug in numbers bigger than or equal to positive 3/2. Sometimes you can be asked to think about these problems backwards. And typically what's always written in the directions, even though it doesn't say that here, is that you want to decompose this into two functions, but you cannot include the identity function. And by that I mean the function y equals x, because that would be really boring, because you would just say y equals x is the inside function, the outside function is this original. Technically that is a correct answer, but it's not an answer you can use on Alex, and it's not an answer you can use on a test, because it's always going to include this directions. You cannot include the identity function, and that's what that means. So let's think about some more interesting things. This has more than one answer, but let's say f of x is equal to g of h of x. We're just going to arbitrarily label these. Typically in these problems they'll sort of pre-label for you what these are. In this labeling, what's considered my inside function? Pause your video and ask yourself. My inside function is h of x. So we're finding g of h of x, and we're saying, had this been our problem, how would this be the result? So just like gut reaction, what seems like it would be the inside function h of x? Pause your video and ask yourself. I bet you either answered 5 minus x squared, or maybe you even answered just the x squared. Both of those would actually be correct. But either way, those are the things that are kind of inside the square root, right? So either of those things is what you would think of as that inside function. Let's just say you called the entirety of 5 minus x squared your inside function. If that's the case, what would be considered your outside function? Your outside function in that case would be the square root of stuff being plugged in. So it'd just be the square root of x. So if you sort of thought a bit this backwards, if I plugged in 5 minus x squared, everywhere I saw an x in g of x, I would be back to the original of f of x. Now let's say you just said x squared was your inside function. How would that change your answer a little bit? Well, in that case, g of x would be equal to the square root of 5 minus x. So that 5 minus part would have also had to be part of the inside function. And then you would have just called your that 5 minus part would have had to be part of your outside function, I meant to say. So that 5 minus part would have to be part of the outside, and then your inside function would just be x squared. Both of these are equally correct answers, and both would be counted as correct both on Alex and on an exam. So there's oftentimes many different answers to these problems, but again, you're not allowed to just say make the inside y equals x, otherwise that would be very boring. Well, not boring. Boring to me. Boring to most of your professors, and hopefully boring to you. Hopefully you want something slightly more exciting than just plugging in y equals x. And there's more than one way to do that. And also, I would highly recommend, if you have any spare time, go ahead and evaluate this to make sure you get what you expect. So if I plug in x squared everywhere I see an x in g of x, I do indeed get this. And in this case, if I plugged in 5 minus x squared everywhere I see an x in g of x, I do indeed get this. The next problem, I would argue, has even more correct answers, but I want you to go ahead and pause your video and try it out for yourself. So first thing you probably wanted to do was arbitrarily label one as your inside function and one as the outside. Just for the sake of clarity, I'm going to keep that labeling the same. And most likely on most tests, you'll be kind of given for you what you're going to label as the inside versus outside function. So in this case, if we're going to call h of x the inside, and g of x the outside, what sort of gut reaction looks like it should be the inside function versus what looks like it should be the outside function. So the simplest inside function you probably could have picked was just like a good old x squared. Some of you might have picked something a little bit spicier than that. Maybe you picked a 4 plus x squared. Maybe you even picked the square root of 4 plus x squared. Maybe you even went all the way as to pick 3 minus the square root of 4 plus x squared. Any of those would be equally correct, and you just want to make sure that, again, when you actually evaluate it, that it works. So I'm going to go ahead and sort of build up actually each of those answers. So let's say, and let me keep those colors the same. I apologize if you're colorblind. Me changing the colors doesn't really do much for you, but hopefully you can still tell how I'm differentiating the notation. So let's say you just called x squared h of x. In that case, what all would you have to include in g of x? Well, you would need the 4 divided by 3 minus the square root of 4 plus x. We didn't label that an x squared because now we're plugging in x squared into g of x to create this function. So that would be the simplest inside function and the most complicated outside function. Now let's change it up a little. Let's say I instead made that inside function 4 plus x squared. What would that get rid of over here? That would get rid of the 4 plus here, because now I'm plugging in the entirety of 4 plus x squared in for x in g of x. And if my outside function was 4 over 3 minus the square root of x, plugging in all of 4 plus x squared would result in that original. Now let's say I instead made it the square root of 4 plus x squared as my inside function. Then I wouldn't need any of that. All I would need for that outside function would be 3 minus x, not 3 minus 3. That would not be allowed for a variety of reasons. 3 minus x, so then I could plug in the square root of 4 plus x squared everywhere I see an x in g, and that would result in that original. You could have even more complicatedly made 3 minus that as that inside function, and then you would just have an x there as your outside function, just 4 divided by that x. I don't think there's really a way you could incorporate the 4 from the numerator into that inside function in a very clean way without then just getting down to the identity function being your outside function, or making a really weird and complicated outside function. But those were kind of all the common answers that I think you might have come up with. As always, please make sure that you take a look at your textbook for more examples and let your instructor know if you have any questions.